Besides just learning how to calculate a dot product, one of the most useful things that we are going to learn that uses a dot product as part of the calculation is a projection. So in application problems, especially in physics, it may be helpful to decompose a vector into two orthogonal vectors. So I've got a graph down here that I'm going to label some pieces on so you can see what I'm talking about. We're going to let u and v be non-zero vectors. If either of them is 0, then the dot product is going to be 0 and there's really nothing to do. So we just assume we're not working with 0 vectors. And more specifically, u is equal to w1 plus w2. And when you see this sum here, you should think parallelogram method. That's how we add vectors together, is we do a parallelogram and draw the diagonal. Understanding that will make this picture look a lot easier. W sub 1 is going to be parallel to vector v, and w sub 2 is orthogonal to vector v. So in my diagram down here, vector u is the diagonal of w sub 1 and w sub 2. If we were to add w sub 1 and w sub 2 together, we would get u. Vector v is this other horizontal vector, but it's much longer. So we're using v for its direction, but not necessarily its magnitude. W sub 1 will have the same direction as v, but it's going to use a magnitude that's appropriate to make this parallelogram so that u can be the diagonal. So what we're going to start with is we're going to start with u and we're going to start with v. And we're going to be asked to calculate w sub 1 and w sub 2. So w sub 1 is called the vector projection of u onto v. One way that you can think of that, and I think is really helpful, is think of it as a shadow. If you were flashing a light so that u casts a shadow onto v, that is what creates our w sub 1. So we're casting this shadow of u down onto v, because u and v will be given at the beginning of the very beginning of the problem. And what that's going to create is this shadow, which is w sub 1. W sub 2, we said, is the vector projection orthogonal to v. So one nice thing about these projections is it's not just going to be a parallelogram, but more specifically, it's always going to be a rectangle. So that's going to be really helpful. So if we're given vector u and vector v, we could calculate this projection, w sub 1, and it's written very similarly to the way that we write a log in algebra class, where v is a subscript. So remember, if we were going to do log base 3 of 5, the 3 is written as a subscript on the log. And in this notation we're using for projection, the v is written in the subscript position after projection. So we're doing the projection of u onto v. So you read the bigger one first and the smaller one second. The way that we calculate that is we do the dot product between u and v, and then we divide by the magnitude of v squared. This is going to give us the appropriate scalar to scale v so that it will create w sub 1 for us. But going back to something I said just a minute ago, we're using v for its direction, but we are not using it for its magnitude. So we really could break some of these pieces up. Anytime we use a vector for its direction but not its magnitude, we transform it to a unit vector. So if we just pull one of those magnitude v's out and stack it with our vector v, we see a unit vector in the direction of v. And that is something that we see a lot when we're using a vector for its its direction, but not its magnitude. What we're left here in the parentheses at the front, this is called the scalar projection of u onto v. All this does is it tells us how long w sub 1 is. So it's the magnitude of w sub 1. And it's called the scalar projection. It's doing a projection, but it's just giving us back a scalar. It's just giving us back how long that new vector w sub 1 is. And then to calculate w sub 2, which is our vector component orthogonal, since we said just a second ago that u is w sub 1 plus w sub 2, u is going to be given. We just had a formula to calculate w sub 1. So to calculate w sub 2, we could just manipulate that equation algebraically and subtract the w1 over to the other side. To get that orthogonal component, we just do our vector u minus our w sub 1. So let's try an example. We want to find the vector projection of u onto v. That's w sub 1. We want to find the scalar projection of u onto v. That's the magnitude of w sub 1. And we want to find the vector component of u orthogonal to v. That is w sub 2. Vector u in this example is going to have components 5, 7, and vector v is going to have components 9, 1. And I tried to keep this first example fairly simple so that we can draw it kind of like the diagram I gave you earlier and see if everything's matching up with what we think it should be. So I'm going to start by drawing these two vectors. U is 5, 7, v is 9, 1. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. So there's our vector u. And vector v is 9, 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then just up a little bit. So these vectors are not orthogonal to each other, and that's perfectly fine. They don't need to be. But what we want to do is we need to think of u as being the diagonal of the box that's created between w sub 1 and w sub 2. And we know w sub 1 is in the same direction as v. And also w sub 1 and w sub 2 have a 90-degree angle between them. So if you think about shining a light on u to see what kind of shadow it's going to make on v, you always want to connect them so that they make a 90-degree corner. And then the origin out to that point is our w sub 1. And then whatever is orthogonal to this, that would make u be the diagonal, is our w sub 2. So it's a little sloppy, but you see I've made a rectangle here in blue. The adjacent sides of that rectangle are w sub 1 and w sub 2, and the diagonal is u. W sub 1 will always be on top of v. So we're using v for its direction, but not its magnitude. So it looks like the answer should be about 1, 2, 3, 4, maybe 6 and then a half, or 6 2/3. And then w sub 2 looks like it might be about -1/6, possibly. So we can kind of get an idea of what's going on with the picture here, but the picture can be kind of tricky to draw. But let's actually just do the calculation. So the first one we were asked for is the projection of u onto v. So the way that we write that is PROJ of u, and then onto v is little subscript v. The calculation for this is u dot v over the magnitude of v squared. This is going to give us a scalar that we can use to adjust the length of v so that it matches up with w sub 1. This is what we're trying to get. Since we know the components for u and v, we can do all of these calculations pretty easily. Trying to scroll down just a tiny bit and it's not letting me. So u is 5.7, v is 9.1. I'm just going to move it down. So we want u dot v. So remember, that's just where we multiply corresponding components. So 5 times 9 plus 7 times 1. In our denominator, we want the magnitude of v. Remember, the formula for magnitude has a square root, but then we're going to square it. So really, they're just going to cancel each other out and leave us with whatever that radicand is. But to do magnitude, we do the sum of the squares of our components. And then we want to multiply this, whatever this scalar is, through into our v. So this is going to be 45 plus 7, which is 52. 9 squared is 81, plus 1 is 82, and the square root cancel each other out. This gives us the scalar that we need to use on v to transform v into w sub 1. So this is just 52 over 82, which we can simplify. I'll simplify it in just a minute. We want to distribute that into vector v, which has components 9, 1. 52 over 82, let's see if we cut those in half, we get 26 over 41. And I think 41's prime, so there's not anything else we can do there. But now if we distribute, we're going to get 26 over 41 times 9, which is 9 times 6 is 54. 9 times 2 is 18. Plus 5 more is 23. Now, these really weird fractions are not very helpful when graphing. So if we want to see if our graph is accurate at all, we could change these to decimals just to get an idea of where exactly this would be plotted. And this is about 5.7 and 0.6. So this is our guess for w sub 1, the projection of u onto v. Let's see if that matches up with our graph. 5.7, 0.6. So 1, 2, 3, 4, 5. Yep, we went about 5.7 units out, and we went about 0.6 units up to get our w sub 1. So that's matching up pretty good with what we were guessing on our graph. So we got the first piece done. The scalar projection of u onto v is when we pull one of those magnitude v's out so that we can actually see the unit vector for v, the calculation that's left over there is our scalar projection. So u dot v over magnitude of v is our scalar projection. And all that's going to tell us is how long w sub 1 is. So scalar projection is written as SCAL of vector u onto vector v. So very similar to how we write projection, but this time we just need u dot v over magnitude of v. We have already said that u dot v was 52. And magnitude of v we did as well, but this time we're not squaring it. So we're going to leave it as square root of 82. And if you want to, you can again change this to a decimal to get an idea of how it's matching up with our graph. And it's about 5.7 units long. So it would be the same thing as if we just did the magnitude of W sub 1. There are some more decimals after, so it shouldn't be exactly the same as what we're getting, 5.74244. So that 0.6 that we're moving vertically is not contributing much. But this is our scalar projection of u onto v. It tells us how much of vector v we need to use. So the orthogonal component of u onto v is our w sub 2, and we get that just by doing u minus w sub 1, and we know both of those right now. U was 5.7, right? Yep, U was 5.7. And we just calculated W sub 1 to be 234 over 41. I'm using the exact values, so I'm going to use the fractions. And to subtract vectors, we just subtract component-wise. So subtract your two first components and subtract your second components. And I'm going to use my calculator to help me. And for my first component, I get negative 29 over 41. For my second component, I am getting 261 over 41. This doesn't help me a whole lot in terms of graphing. That is our answer for W sub 2, but I'm going to change it to decimals just so we can compare it to the picture that we had above. This is about negative 0.7 and 6.3. So I'm going to go back up to the graph and see if that makes sense. So negative 0.7 means we're going to move left. Yep, we moved left. And then 6.3, 1, 2, 3, 4, 5, 6. So I didn't make this quite long enough. It goes left 0.7, up 6.3, which matches up pretty closely to what we got. Vector projections are notoriously one of the difficult things for students to wrap their heads around. They're doing a whole bunch of calculations. A lot of people have no trouble memorizing the formula, but what exactly is going on and why we're doing it can be really confusing. So just think of this as somebody has already done an addition problem and came up with u. And our goal is to break it back up into the two vectors that were added together to create it. Those two vectors will always be at a 90-degree angle to one another. And one of the vectors we will be given the direction for. So we'll be given vector v. So I know one of the vectors in that rectangle points in the direction of v. And if I know the direction for that one, then I will automatically know what 90 degrees away from that is, and then we jump to our calculations. So we're starting with the final answer of an addition product, and we're trying to break it back apart into its two pieces. This is going to be really helpful when we start talking about acceleration, because acceleration measures change in velocity, and velocity has two components. It's got magnitude and direction. So if we want to measure the change in velocity, we could actually split it apart and say, well, I want to calculate how my speed is changing, and I want to calculate how my direction is changing. So we take our acceleration vector and we're breaking it into two pieces. How much of the acceleration is going towards changing our speed, and how much of the acceleration is going towards changing our direction. And that's one really important application that you'll see later on we use the projection for.